Swayam Prabha. Digital India. Educated India.
Good morning, all of you. Welcome to this fluid mechanics course. Today we are in the third lecture of fluid statics. Already in the first two lectures, we have already seen the concepts of pressures and forces acting on fluids at rest, scales of pressure measurement, the basics of pressure measuring instruments. We have also seen the hydrostatic forces on submerged surfaces, that is plane and curved surfaces, in our second lecture. So in today's lecture, we are going to look and understand the concepts of buoyancy on floating bodies, the stability of submerged and floating bodies. We will also look at the rigid body rotation of fluid, although the fluid is rotating, but how it behaves like a rigid body. So we will see that. Now, coming to understand the buoyancy, first of all, we know an object, when it is submerged in a liquid, is going to experience a force, and it will experience an upward force, a buoyancy force, that you might have realized whenever you get into water or a swimming pool or any river or pond. You will feel some kind of lightness, or you will feel that your weight is not really that much. You will feel slightly lighted, and that is nothing but the force that is acting on you, which is nothing but buoyancy force. Let us understand this buoyancy force by analyzing the pressure acting on the body that is submerged in the water. So, if we look at this body, which is ABCD, is a sphere, or let us say it's a cylinder. So ABCD is a cylinder that is submerged in the fluid, and the fluid free surface is here, and you have the distance y, that is from the free surface of the fluid to the center of the cylinder. Now, if we look at the fluid, will have some density, that is, let us say rho. So accordingly, the unit weight of the fluid will be rho g gamma, and the pressure we can find out at any depth or any distance y. So that is rho g y. So now, if we calculate the upward force, so upward force acting on the fluid element is going to be the force that is acting total, or the net upward force that is acting on the body is equals to the force acting upward minus the force acting downward. So let us say, if we assume that the total surface, the pressure is acting, there is a pressure acting on all sides of this surface. So there is forces, there is a pressure acting upward, there is a pressure acting downward. So we have to equate that and find out what is the net upward pressure that is acting on this body. So if we, as I said, if we separate this out into two components, one is FP2, one is FP1, and the FP2 is the force, or the total integration of pressure acting upward, and FP1 is acting downwards. Okay. So we will now try to find out how this force is acting. So let us consider the upper half of this cylinder, which is nothing but your ADC. So if you look at this figure and we will consider the surface ADC, then we will calculate what is the total force acting on this. So we know that the total force acting on a curved surface, total vertical force acting on a curved surface, is equal to the mass of fluid, or the weight of fluid standing on top of the curved surface up to the free surface. So now, if we find out what is the weight of this liquid mass, so I will take this rectangle and I will subtract this semicircle, then I will get this area. Once I get the area, I can multiply that with unit width that is perpendicular to the plane or to the screen that you see. So that is my volume, and to that volume, if I multiply the unit weight, I'll get the weight of that liquid. Because I am considering a cylinder, so cylinder is I'm taking the unit length of the cylinder. So unit width across or perpendicular to the surface is considered. So it is 1. We can calculate now. So what is this rectangle? Rectangular is nothing but your diameter of the cylinder, that is d, multiplied by y. Y is the depth up to the center. So dy minus pi d square by 8. So pi d square by 4 is the total area. Half of that is pi d square by 8. And if I subtract that, then I will get this area which is asked here. Once I get that area, multiply that with 1, which is not shown here in this equation expression, but it is always multiplied with 1 so that you get the volume of that liquid. Now that volume is multiplied with gamma. That gives you the force acting downwards, that is on the surface ADC. So similarly, now let us look at the force acting upwards, which is Fp2. And Fp2 is acting on what? Acting on ABC, the surface, curved surface ABC. Now that is equals to, again, the same principle. The vertical force acting on a curved surface is equal to the equivalent weight of the liquid standing on top of the curved surface. So basically it is due to the pressure acting on the curved surface. Now for that I will be able to get this surface, which is nothing but the surface that is hashed here. So starting from this, I will take this whole thing is the liquid that is standing on this curved surface. Then you may question me that the cylinder is completely solid, let us say, or it is a impermeable surface, so there cannot be any ingress of water into that. So how do you consider this part? Yes. So now to make you understand, let me say I will consider any small strip of surface here. Let us say I will consider this surface. Now if I consider this surface, then I want to find out what is the pressure acting here. So the pressure acting at this point outside this ABC surface is nothing but your gamma, let us say y1 here. So if I will consider this, what is this? This is dA. Okay. So let us say this surface is nothing but your delta A or delta S, whatever you want to tell. So that surface, unit surface, I am taking the distance over that, and this mass of water or this weight of this water, this column of water, is exerting the pressure on this. So force. So this is nothing but equivalent to this strip of water. Okay. So now this strip, what we have shown, okay, is basically exerting the pressure in the upward direction. So instead of showing it outside like this and integrating, I am just showing it for quick understanding that this weight of water or this volume of water is exerting the force on this surface, but that is acting upward. Alright. So now this force is acting somewhere here, and if I take that force, and the net force is going to act the upward direction. So that we can calculate by taking the volume, that is dy plus pi d square by 8 multiplied by 1 multiplied by gamma. So this becomes your force that is acting upwards. This is the force acting downwards. Okay. Now if we take the combination of these two, we can find out the net upward force that is acting on the cylinder. So that we have done here. Fp2 minus Fp1 is equals to pi d square by 4 multiplied by 1, which is not shown there. So you have pi is 1 multiplied by this area. So that multiplied by gamma, which is the weight of the fluid displaced by unit length of cylinder. That unit is here. Okay. So you have the area of the cylinder here. So unit length of the cylinder is going to displace this liquid, and that weight of that liquid is nothing but the force that is acting on this body in the upward direction. So this is the buoyancy force which is acting on this body. So buoyancy force is equal to the weight of the fluid displaced by the submerged body. So finally what we understood, if I have some net force, that is buoyancy force Fb, then I have the weight of the body. So finally we understood the buoyancy force that is acting upwards is equal to weight of the fluid displaced by the submerged body, and that has to be balanced by the, or the weight of the body has to be balanced by this liquid. Once we have understood what is buoyancy, if you look at, once the body is fully submerged, the buoyant force is independent of depth. If you look at the figure again, here this expression what we have written is not dependent on depth, it is completely dependent on the body, which is, or the volume of the body. So we have understood is the fluid displaced by the submerged body. So if it is completely submerged, the complete volume of the body is submerged, so it is the volume that has been displaced. Doesn't matter whatever depth you are going to vary or whatever depth the body is submerged, the volume displaced is going to be same. So once the body is fully submerged, the buoyancy force is going to be independent of the submergence depth. Okay. The upward force acts through the center of gravity of the submerged object. And for a body in a liquid with free surface, if the weight of the body is less than that of the same volume of liquid, it will rise and float on the surface, so that finally the condition W equals to Fp will be satisfied. So the buoyancy force is acting upward and weight of the body is acting downward. So for stability or for a certain static equilibrium condition, the weight that is acting downward and force that is buoyancy force that is acting upward, both have to be same. Now if, let us say, the body is is floating, then what is the condition? The weight of the body is less than the same volume of liquid uh, that is displaced by the body. So if I have some body here and it is displacing some amount of fluid, this is my free surface, and this body which is liquid, which is displacing the liquid, and that gives rise to Fb, and I have the weight of the body that is acting downward, W. So now if W is less than Fb, then what will happen? Fb is going to push it upward. So it will keep on pushing upward till the point that the body comes to a position where the weight of the body and the weight of the liquid displaced by the body both are same, and only then it will be stable or it will remain there. So the body will be floating. Sometimes you will find the body will be completely floating on the top of the water. So maybe a very minor section of the body might be submerged, a very small section. So that is telling that the body is so light, so only a small amount of fluid is displaced by the body, or the body is partially submerged, only a minor section of the body is partially submerged. So you see the complete. Let us say you have a football or a ball that you are playing with in the water. So maximum or majority portion of the ball is floating on the water. So the weight is very light or weight is very less. So it doesn't require to displace much of the liquid to float. So that's what is the buoyancy force we have understood. Now let us look at the stability of submerged bodies. So we have now two different types. One is submerged, one is floating. So we'll first look at the stability of submerged bodies. The equilibrium of a body submerged in a liquid requires the weight of the body acting through the center of gravity to be collinear with the equal hydrostatic lift or buoyancy acting through the center of buoyancy. So center of gravity and center of buoyancy are not necessarily the same points. Center of gravity is the CG of the body. So it depends on the shape of the body and density of the submerged body. Whereas the center of gravity is the center of buoyancy is the center of the fluid volume that is displaced. Now, the density is different in this case, so the center of buoyancy would be different. So now, if we see the first figure, if we see this first figure, you can observe that you have a submerged body here, which is shown here, and this is completely submerged because you have the free surface here, and here we have the center of buoyancy that is marked with symbol B, and the center of gravity is marked with G. So W is acting downwards, buoyancy force Fb is acting upwards. And if these two are acting, or the line of action is same, okay, then what will happen? The body is going to be stable equilibrium. Why is it so? If you find that the line of action is same and B is at a higher elevation or B is above the G, then the forces are pulling it. So it is pulling each other. So this kind of tension. So the body is under stable condition. Now we will be able to look at various different conditions. One is stable equilibrium, unstable equilibrium, and neutral equilibrium. So in general, the body is not homogeneous, and its distribution of mass over the entire volume and the location of center of gravity does not coincide with the center of volume, that is the center of buoyancy, that is V. So depending upon the relative location of this G and V, the floating body can attain different state of equilibrium. As I said, the first one is the stable equilibrium, and if you see, in case of stable equilibrium, we have this B above and G below, and let us say you go and displace this body little bit, and if you displace this body in the right clockwise direction, what is going to happen? Your body will be tilted and the center of buoyancy is going to shift because you have tilted the body, so the volume has shifted and its buoyancy is going, center of buoyancy will shift and center of gravity will shift this way. So now because of this shift, what is going to happen? There is a change in the line of action. So this line of action is here and your line of action is here. So they both are going to generate a moment in the anticlockwise direction because Fp is acting upward. So about the midpoint or center line, it will create a moment in the anticlockwise direction. So this anticlockwise moment is trying to restore the body into body to its natural position or initial position. So initial position is going to be achieved even if you displace the body, and that is going to ensure that the body is going to be again in equilibrium, and that's where we call this system as stable equilibrium. Now let us look at the next statement, that is unstable equilibrium. In this case, if the center of buoyancy is below, center of gravity is above, then what will happen? Your W is acting downwards, buoyancy force is acting upwards, and they are acting on the same line of action. So as long as the body is in this position, it is stable. But the moment you start disturbing the body or you tilt this body, then what will happen? The W is acting here at G and B is acting up, FB is acting upward at B. They will create a clockwise moment. So you have displaced the body in the clockwise direction and the moment is acting again in the clockwise direction. So it will further displace the body and the body is going to tilt further and it will become unstable as it goes. So it might, after some time, you will find the body will completely move upside down. So that condition is called unstable equilibrium. So it will be in equilibrium till this line of action is not disturbed and it is same. So there is no moment acting. The immediate instant when you have disturbed this body, there is going to be a moment which will disturb this body, so it is going to be unstable. Now there is another condition which is called neutral equilibrium. Now let us say that gravity and buoyancy both are acting at the same point, or G and B coincide at the same point. So what will happen? There is no moment due to these forces, whatever position it may take. So you may change or rotate this body to some extent. The axis of this body has moved, but the forces are acting at the same point, so they don't generate any moment. So eventually what will happen? It will remain in that position wherever or whatever displacement you have made. So if you tilt this body again to another position, it will remain in that position. Okay. So this condition is called neutral equilibrium. So we have seen that the submerged body can have three different states, that is equilibrium, stable equilibrium, unstable equilibrium and neutral equilibrium, and these depend on the relative position of the center of gravity of the body and center of buoyancy. Alright, now let us look at the floating body stability. So floating body stability is slightly different compared to the submerged body. So let us say you have this figure here which shows a typical vessel or ship. So this vessel is floating in water and you have this vessel which is submerged partially and it has some portion which is above water. So basically you have a draft, or the section which is submerged, that we call it as draft. So from this point to this point we call it draft. Depending on the weight or the load on the vessel, the draft can change, and this draft will be maintained to a certain extent that the total or the vessel is stable at all conditions. So there might be a lot of forces, other forces acting, there might be waves coming, there will be current in the sea, there will be wind. So all these forces are going to act on this vessel and there is a load being carried by this vessel. So in all these conditions, this vessel has to be stable, which is floating. So now we are not really applying all the forces here. We are just assuming that the fluid is static here, or this is a static tank, and in that there is a vessel which is floating. And we want to first understand the simple concept. So in this case, the weight of this vessel is acting at this point G, that is W, and B is acting at this point, that is the center of buoyancy. And as we have already seen that there can be conditions, it's not necessary that always G is below B. So it can be a situation where center of gravity is above the center of buoyancy. So in that case, we know that if it's a submerged body, then we are getting into unstable equilibrium. But here we have to ensure that the body is stable, because if it is unstable, then the complete vessel is going to topple and it will lead to disaster. So now let us analyze. Let this line of action of the buoyancy force, which is always vertical, act through B dash, intersect the axis BG, that is initially. So I'll just draw this little bit clearer here. So this line, if I draw, sorry, the line has to pass through this B. So the line BG is the vertical line. So initial BG, that is shown here, and if the body is tilted, okay, if the body is tilted in the clockwise direction, then your point B is going to shift rightwards, because you have larger mass or volume displaced on the right side, less volume is displaced on the left side. So the center of volume is going to be moved to the right side. So you have the point B dash here. Now if you draw a vertical line to B dash, and that goes and intersects this line BG at some point, let me call that point as M. So which is denoted as M, and this line is called, or this point is called metacenter.